Chapter 5. Higher Order Functions. There are two ways of constructing a software design. One way is to make it so simple that there are obviously no deficiencies, and the other way is to make it so complicated that there are no obvious deficiencies. C. A. R. Hoare, 1980 ACM Turing Award Lecture. A large program is a costly program, and not just because of the time it takes to build. Size almost always involves complexity, and complexity confuses programmers. Confused programmers, in turn, introduce mistakes, bugs, into programs. A large program then provides a lot of space for these bugs to hide, making them hard to find. Let's briefly go back to the final two example programs in the introduction. The first is self-contained and 6 lines long. The second relies on 2 external functions and is 1 line long. Which one is more likely to contain a bug? If we count the size of the definitions of sum and range, the second program is also big, even bigger than the first, but still I'd argue that it's more likely to be correct. This is because the solution is expressed in a vocabulary that corresponds to the problem being solved. Summing a range of numbers isn't about loops and counters, it's about ranges and sums. The definition of this vocabulary, the functions sum and range, will still involve loops, counters, and other incidental details, but because they are expressing simpler concepts in the program as a whole, they are easier to get right. Abstraction. In the context of programming, these kinds of vocabularies are usually called abstractions. Abstractions give us the ability to talk about problems at a higher or more abstract level without getting sidetracked by uninteresting details. As an analogy, compare these 2 recipes for pea soup. The first goes like this. Put 1 cup of dried peas per person into a container, add water until the peas are well covered. Leave the peas in water for at least 12 hours. Take the peas out of the water and put them in a cooking pan. Add 4 cups of water per person. Cover the pan and keep the peas simmering for 2 hours. Take half an onion per person. Cut it into pieces with a knife. Add it to the peas. Take a stalk of celery per person. Cut it into pieces with a knife. Add it to the peas. Take a carrot per person. Cut it into pieces with a knife. Add it to the peas. Cook for 10 more minutes. And this is the second recipe. Per person, 1 cup dried split peas, 4 cups water, half a chopped onion, a stalk of celery, and a carrot. Soak peas for 12 minutes, simmer for 2 hours, chop and add vegetables, cook for 10 more minutes. The second is shorter and easier to interpret, but you will need to understand a few more cooking-related words such as soak, simmer, chop, and I guess vegetable. When programming, we can't rely on all the words we need to be waiting for us in the dictionary. Thus, we might fall into the pattern of the first recipe. Work out the precise level, or the precise steps the computer has to perform one by one, blind to the higher level concepts they express. It is a useful skill in programming to notice when you're working at too low a level of abstraction. Abstracting repetition. Plain functions, as we've seen them so far, are a good way to build abstractions, but sometimes they fall short. It is common for a program to do something a given number of times. You can write a for loop for that, like this. Can we abstract doing something n times as a function? Well, it's easy to write a function that calls console log n times. But what if we want to do something other than logging the numbers? Since doing something can be represented as a function and functions are just values, we can pass our action as a function value. We don't have to pass a predefined function to repeat. Often it's easier to create a function value on the spot instead. This is structured a little like a for loop. It first describes a kind of loop and then provides a body. However, the body is now written as a function value, which is wrapped in the parentheses of the call to repeat. This is why it has to be closed with a closing brace and closing parentheses. In cases like this example, where the body is a single small expression, you could also omit the braces and write the loop on a single line. Higher order functions. Functions that operate on other functions, either by taking them as arguments or by returning them, are called higher order functions. Since we have already seen that functions are regular values, there is nothing particularly remarkable about the fact that such functions exist. The term comes from mathematics, where the distinction between functions and other values is taken more seriously. Higher order functions allow us to abstract over actions, not just values. They come in several forms. For example, we can have functions that create new functions. We can also have functions that change other functions. We can even write functions that provide a new type of control flow. There is a built-in array method for each that provides something like a for-of loop as a higher order function. Script dataset. One area where higher order functions shine is data processing. To process data, we'll need some actual example data. This chapter will use a dataset about scripts, writing systems such as Latin, Cyrillic, or Arabic. Remember Unicode, the system that assigns a number to each character in a written language from Chapter 1? Most of these characters are associated with a specific script. The standard contains 140 different scripts, of which 81 are still in use today and 59 are historic. Though I can fluently read only Latin characters, I appreciate the fact that people are writing texts in at least 80 other writing systems, many of which I wouldn't even recognize. For example, here's a sample of Tamil handwriting. The example dataset contains some pieces of information about the 140 scripts defined in Unicode. It is available in the coding sandbox for this chapter as a scripts binding. The binding contains an array of objects, each of which describes a script. Such an object tells us the name of the script, the Unicode ranges assigned to it, the direction in which it is written, the approximate origin time, whether it is still in use, and a link to more information. The direction may be LTR for left to right, RTL for right to left, the way Arabic and Hebrew texts are written, or TTB for top to bottom as with Mongolian writing. The ranges property contains an array of Unicode character ranges, each of which is a two-element array containing a lower bound and an upper bound. Any character codes within these ranges are assigned to the script. The lower bound is inclusive, code 994 is a Coptic character, and the upper bound is non-inclusive, code 1008 isn't. Filtering arrays. If we want to find the scripts in the dataset that are still in use, the following function might be helpful. It filters out elements in an array that don't pass a test. The function uses an argument named test, a function value, to fill a gap in the computation, the process of deciding which elements to collect. Note how the filter function, rather than deleting elements from the existing array, builds up a new array with only the elements that pass the test. This function is pure. It does not modify the array it is given. Like for each, filter is a standard array method. The example defined the function only to show what it does internally. From now on, we'll use this like this instead. Transforming with map. Say we have an array of objects representing scripts, produced by filtering the scripts array somehow. We want an array of names instead, which is easier to inspect. The map method transforms an array by applying a function to all of its elements and building a new array from the return values. The new array will have the same length as the input array, but its content will have been mapped to a new form by the function. Like for each and filter, map is a standard array method. Summarizing with reduce. Another common thing to do with arrays is to compute a single value from them. A recurring example, summing a collection of numbers, is an instance of this. Another example is finding the script with the most characters. The higher order operation that represents this pattern is called reduce, sometimes also called fold. It builds a value by repeatedly taking a single element from the array and combining it with the current value. When summing numbers, you'd start with the number 0 and for each element add that to the sum. The parameters to reduce are, apart from the array, a combining function and a start value. This function is a little less straightforward than filter and map, so take a close look at it. The standard array method reduce, which of course corresponds to this function, has an added convenience. If your array contains at least one element, you are allowed to leave off the start argument. The method will take the first element of the array as a start value and start reducing at the second element. To use reduce twice to find a script with the most characters, we can write something like this. The character count function reduces the ranges assigned to a script by summing their sizes. Note the use of destructuring in the parameter list of the reducer function. The second call to reduce then uses this to find the largest script by repeatedly comparing two scripts and returning the larger one. The Han script has more than 89,000 characters assigned to it in the Unicode standard, making it by far the biggest writing system in the dataset. Han is a script sometimes used for Chinese, Japanese, and Korean text. Those languages share a lot of characters, though they tend to write them differently. The US-based Unicode consortium decided to treat them as a single writing system to save the character codes. This is called Han unification and still makes some people very angry. Composability. Consider how we would have written the previous example, finding the biggest script without higher order functions. The code is not that much worse. There are a few more bindings and the program is 4 lines longer, but it is still very readable. The abstractions these functions provide really shine when you need to compose operations. As an example, let's write code that finds the average year of origin for living and dead scripts in the dataset. As you can see, the dead scripts in Unicode are, on average, older than the living ones. This is not a terribly meaningful or surprising statistic, but I hope you'll agree that the code used to compute it isn't hard to read. You can see it as a pipeline. We start with all scripts, filter out the living or dead ones, take the years from those, average them, and round the result. You could definitely also write this computation as one big loop. However, it's harder to see what was being computed and how, and because intermediate results aren't represented as coherent values, it'd be a lot more work to extract something like average into a separate function. In terms of what the computer is actually doing, these two approaches are also quite different. The first will build up new arrays when running filter and map, whereas the second computes only some numbers, doing less work. You can usually afford the readable approach, but if you're processing huge arrays and doing so many times, the less abstract style might be worth the extra speed. Strings and character codes. One interesting use of this dataset would be figuring out what script a piece of text is using. Let's go through a program that does this. Remember that each script has an array of character code ranges associated with it. Given a character code, we could use a function like this to find the corresponding script, if any. The sum method is another higher order function. It takes a test function and tells you whether that function returns true for any of the elements in the array. But how do we get the character codes in a string? In Chapter 1, I mentioned that JavaScript strings are encoded as a sequence of 16-bit numbers. These are called code units. A Unicode character was initially supposed to fit within such a unit, which gives you a little over 65,000 characters. When it became clear it wasn't going to be enough, many people balked at the need to use more memory per character. To address these concerns, UTF-16, the format also used by JavaScript strings, was invented. It describes most common characters using a single 16-bit code unit, but uses a pair of two such units for others. UTF-16 is generally considered a bad idea today. It seems almost intentionally designed to invite mistakes. It's easy to write programs that pretend code units and characters are the same thing, and if your language doesn't use two-unit characters, that will appear to work just fine, but as soon as someone tries to use such a program with less common Chinese characters, it breaks. Fortunately, with the advent of emoji, everyone has started using two-unit characters, and the burden of dealing with such problems is more fairly distributed. Unfortunately, obvious operations on JavaScript strings, such as getting their length through the length property and accessing their content using square brackets, deal only with code units. JavaScript's car_code_at method gives you a code unit, not the full character code. The code_point_at method added later does give a full Unicode character, so we could use that to get characters from a string. But the argument passed to code_point_at is still an index into the sequence of code units. To run over all characters in a string, we need to deal with the questions of whether a character takes up one or two code units. In the previous chapter, I mentioned that a for/of loop can also be used on strings. Like code_point_at, this type of loop was introduced at a time when people were acutely aware of the problems with UTF-16. When you use it to loop over a string, it gives you real characters, not code units. If you have a character, which will be a string of one or two code units, you can use code_point_at0 to get its code. Recognizing text. We have a character script function and a way to correctly loop over characters. The next step is to count the characters that belong to each script. The following counting abstractions will be useful there. The countBy function expects a collection, anything that we can loop over with for/of, and a function that computes a group name for a given element. It returns an array of objects where each name a group and tells you the number of elements that were found in that group. It uses another array method, find, which goes over the elements in the array and returns the first one for which a function returns true. It returns undefined when it finds no such element. Using countBy, we can write the function that tells us which scripts are used in a piece of text. The function first counts the character by name, using character script to assign them a name and falling back to the string none for characters that aren't part of any script. The filter call drops the entry for none from the resulting array since we aren't interested in those characters. To be able to compute percentages, we first need the total number of characters that belong to a script, which we can compute with reduce. If we find no such characters, the function returns a specific string. Otherwise, it transforms the counting entries into readable strings with map and then combines them with join. Summary. Being able to pass function values to other functions is a deeply useful aspect of JavaScript. It allows us to write functions that model computations with gaps in them. The code that calls these functions can fill in the gaps by providing function values. Arrays provide a number of useful higher-order methods. You can use for each to loop over the elements of an array. The filter method returns a new array containing only the elements that pass the predicate function. You can transform an array by putting each element through a function using map. You can use reduce to combine all the elements in an array into a single value. The sum method, whether any element matches a given predicate function, while find finds the first element that matches a predicate. Exercises. Flattening. Use the reduce method in combination with the concat method to flatten an array of arrays into a single array that has all the elements of the original arrays. Your own loop. Write a higher order function loop that provides something like a for loop statement. It should take a value, a test function, an update function, and a body function. Each iteration, it should first run the test function on the current loop value and stop if that returns false. It should then call the body function, giving it the current value, and finally call the update function to create a new value and start over from the beginning. When defining the function, you can use a regular loop to do the actual looping. Everything. Arrays also have an every method analogous to the sum method. This method returns true when the given function returns true for every element in the array. In a way, sum is a version of the OR operator that acts on arrays, and every is like the AND operator. Implement every as a function that takes an array and a predicate function as parameters. Write two versions, one using a loop and one using the sum method. Dominant writing direction. Write a function that computes the dominant writing direction in a string of text. Remember that each script object has a direction property that can be LTR, left to right, RTL, right to left, or TTB, top to bottom. The dominant direction is a direction of a majority of the characters that have a script associated with them. The character script and count by functions defined earlier in the chapter are probably useful here.